Good morning once again. It's my pleasure to welcome you to the second session of our IPPW webinar series. My name is Jim Cutts. I'm from JPL, and I'm also a longtime member of the IPPW community. At this time, I would also like to introduce my co-host for the session, Jacob Israelowitz, also of JPL. First, a few words about the IPPW workshop. For those of you who are new to the International Planetary Probe Workshop, I'd like to start by saying a few words about what we do. Each year since 2003, we've held a week-long workshop and a short course focused on the exploration of planets with probes, landers, and yes, aerial vehicles for our community of scientists, engineers, and technologists. The workshop has alternated between the US and Europe, and this year would have been held in Monterey, California in 1 month's time, but for the intervention of COVID-19. So instead this year, we've organized a series of 6 webinars, 2 weeks apart, most of them timed for the convenience of our members in the continental US, and then east across Europe, the westernmost time zones in Russia and India, where it is now 8:30 p.m. And we already have members from Russia and India who are participating today. While we hope that some of our other Asia-Pacific members will be burning the midnight oil to join us today, we've scheduled session 5 at a time convenient for that region, where we expect to have participants from Japan, South Korea, and Australia. And then, of course, when we once meet again in person, it will be in Japan in September of 2021. Now, today's topic, aerial exploration of Mars, Titan, and Venus, is of particular interest to me. As a result, I'm delighted we have 3 of the leading engineers in the nation and indeed the world to describe how they plan to address the unique challenges of aerial exploration for each of these very different bodies. So Jacob, perhaps you could say a few words of introduction.
Thank you, Jim. Mars, where the Mars helicopter recently named Ingenuity will fly, has a tenuous atmosphere much like the Earth's stratosphere. How, you might ask, can a helicopter fly under these conditions? Bob Ballaram of JPL is going to explain the design of this Mars helicopter. Bob will also describe how the Mars 2020 rover will place the Ingenuity on the surface of Mars from where it can embark on its first epic flights approximately a year from now. Titan, the target for the Dragonfly mission, is the fascinating satellite of Saturn. Titan is the only moon with a dense atmosphere, and a thick atmosphere at that, extending hundreds of kilometers above the surface. So how can we fly a rotorcraft under these conditions with so little solar power and frigid temperatures of -200 Celsius? Ken Hibbard of the Johns Hopkins Applied Physics Laboratory is going to provide the answer to these questions and describe preparation to launch Dragonfly on its long trip to Titan in April 2026. Venus, the subject of the last talk, presents very different challenges than Mars or Titan. It has a surface hot enough to melt lead and corrosive clouds of sulfuric acid. However, Venus is also the only one of these target bodies where aerial vehicles have flown before, back in 1985. But after a long hiatus, Jeff Hall of JPL and his team are working on how we can return to Venus with the powerful exploration capability sometime during the next decade. Each of our speakers today will speak for approximately 20 minutes, and at the end of the session, we will have allocated time for Q&A. You will need to type your questions, and I encourage you to do so before the talks are complete so that we can move directly into the questions at the end of the session. To streamline things, I will read out the questions and direct them to the appropriate speaker. And now back to you, Jim, to introduce our first speaker.
Thank you, Jacob. Our first speaker is Bob Ballaram. Bob is a principal member of technical staff here at JPL, where he is with the Mobility and Robotic Systems section. At JPL, he's been active in the area of telerobotics technology, development for Mars rovers, planetary balloon aerobot systems. This is where I first got to know Bob almost 2 decades ago. Multi-mission, high-fidelity spacecraft simulators for entry, descent, and landing, as well as for surface mobility. Bob is currently the chief engineer for the Mars helicopter project. Bob?
Thank you, Jim. So yes, just about a year from now, we should be on the surface of Mars, either just getting ready to fly or in the midst of our flight campaign. We launch in July of this year, and there's a technology demonstration to validate the whole technology related to flying on Mars with a helicopter. And we have a small 1.8 kilogram system that's tucked away on the Perseverance rover that will land next February. They will spend some time getting themselves commissioned and being able to drive, and then they'll find a spot to drop us off. And there's a short little video that runs for about 2 minutes that I will show now and narrate through that. So Tim, if you can get that started and put the sound off so that I can talk over it. So that's the Perseverance rover approximately a year from now. And it has just dropped off the helicopter, which has been attached all these months on the belly. And then the rover moves away to uncover our solar panels. At that point, they do a little bit of inspection on us, and we get ready to do some of our own commissioning. The very first step that you'll see there is we have blade locks which keep our blades kind of lined up with the rover so they don't rattle around and move around. And we go through a little sequence to, unlock the blades. So you'll notice that both the upper and lower blades are locked and unlocked. The rover then moves away further to a safe observing distance, at least 100 meters or more, and then we commence our flight. Now, I should just point out that even though this is an animation, the animators actually did look at a lot of our high-fidelity physics simulations, and the particular sort of twitches and behavior of this vehicle as it moves is actually probably quite realistic. We will kick up some dust, and then we take off. Tim, you can put the sound on if you want for a little bit. We also are expecting that the Perseverance rover will be able to image us as we fly, and then we go through a flight. We validate a lot of the forward dynamics, the hover flight. There's obviously a whole onboard navigation system that's exercised. That gets checked out, and then we come back to our landing site. Now, one particular thing to note about this particular tech demo is that since it's really all focused on engineering validation, we're really not carrying any science instruments, but we do have a color camera, which is exactly the same kind of color camera that you have on your cell phone. So we hope to return to Earth some nice color images, but the real major focus is a lot on getting good engineering telemetry so that we can successfully open up aerial mobility for the next generation of helicopters, which there's early work that's going on for those, and I will get to that in the end of the presentation. So with that, next slide, please. Why helicopters? In school, you might have been taught the 3 R's, reading, writing, and arithmetic, but to me, it's reach, range, and resolution. Helicopters can get up close and personal and do close-up signs, standoff signs. They can get to locations which are impossible to reach by rovers, landers. We can have tremendous range. The Mars helicopter, inherently, the aerodynamics of it is such that it could support forward flight at 20 to 30 meters per second. Now, in our technology demonstration, we are keeping the speeds down to a few meters per second, but the vehicles themselves are quite capable of traveling long range for many, many minutes at that speed, covering many kilometers. And then, of course, the instrumentation on the helicopter, future helicopters especially, they will have resolutions comparable to what you have on rovers, things like camera. and but you'll have that. So it's better than an orbiter. It's as good as the rover in terms of resolutions, and you get that kind of imagery and other high fidelity sensor data from up close. So the 3 R's, reach, range, and resolution, sort of motivate helicopters on any planet, I would think. And you've already seen the proliferation of drones here on Earth, and it's precisely for the same 3 reasons. But what does it take to do that on Mars? Next slide, please. Well, we have a challenge, as Jacob mentioned. We have a density that's 1% of that of the Earth's surface. It's like being at 100,000 feet or 33,000 meters here on Earth, and all terrestrial helicopters really typically don't go much more than about 15,000 meters. That's kind of like the record-setting helicopters. Now, we do benefit from the fact that gravity is about 40% of what we have on Earth, so that definitely helps. But still, it's very thin air. It's got all the issues related to low-density airflow, low Reynolds numbers, and all of that has to be successfully overcome in order to have a flying vehicle. Next slide. And of course, this is an obvious statement. It has to be fully autonomous. We are 20 minutes away in terms of light time, and so there's no way you can price take it. Next. One particular challenge that we have had, at least as far as the technology demonstrator goes, is that we are a very small vehicle, and as anybody who's has experienced, if you're small, your area and volume ratios are really not favorable to keeping warm. So we fight the cold right through the night. It can drop down to about minus 90 degrees centigrade at night. In the springtime, that's when our mission is, in the local Mars springtime. And so that's a major challenge for us to keep a lot of our electronics and batteries and things sufficiently warm so that we don't have problems. And in fact, almost 3/4 of our energy budget is devoted to just, heaters and heat to operate and survival heaters and those sorts of things. It's a unique challenge on Mars, made especially tougher by the fact that we're so small as a technology demonstrator. Next slide. And then, of course, it's very easy to conceive of a design that is sort of gossamer-like and thin and can handle the aerodynamics and is light enough to fly on this mission, but it's also got to be a spacecraft, which means that vibrations, G-forces, vacuum and radiation, all the things that you have in a traditional spacecraft, you can't throw mass at it. You have to stay light, but you have to, for example, like all the structural elements on the helicopter are at least a minimum 80 G vibration load, designs, and to hold it so that the blades don't flap around, to experience all the pyroshock events related to release and deployment. These are not things that traditional aircraft designers worry about, but we had to overcome that challenge. Next slide. And finally, we are not just a little CubeSat, all by ourselves or some fairly benign situation. We are on a flagship mission, and we have to be extraordinarily safe to this wonderful rover that's going there and going to be searching for, signs of extant life. We have to be very, very clean for planetary protection. It's not just an aerodynamics design. It's got to be clean of spores and be able to be cleaned. And so there's a whole material selection challenge. There's a whole prove yourself safe to the rover challenge. We are carrying lithium-ion batteries. There's lots of interesting safety-related issues that, again, a traditional drone would probably not pay that much attention to. Next slide. So with that, that's what we ended up with. It's a 1.8 kilogram system. Just as a personal aside, if I had known that it had all these challenges up front, I may not have bitten off this particular project, but we got to the end point. This helicopter is now safely tucked under the rover. It's got its debris shield on, and the next time anybody sees it, it will be on Mars. It's right now on the Cape, part of the launch stacking activities of the Perseverance rover as we get onto our Atlas rocket in July and fly. Next slide. So let me now walk through a little bit of the the various pieces and what some of the technologies are. I'm going to start from the top and work myself clockwise, so you can follow along. Tip to tip, we are a 1.2 meter diameter system, and that's really constrained by the fact that we had to be accommodated on the rover, and that set an upper size limit, which automatically meant that if you factor in the environment and the gravity and the performance you could get, you really can't lift more than about 2 kilograms with those kinds of diameters. It's with our current airfoil design. So very mass constrained, and so we are using a lot of off-the-shelf parts. In the telecommunication system, with the COTS chipset, we've essentially implement an IEEE 802.15.4 protocol. It's a so-called ZigBee protocol. We have a two-node network. One node is the helicopter, and the other node is actually a base station that is bolted onto the rover and serves as the communication pathway back to the rover, which then relays all our information back to Earth to our operators. We have a solar panel. It's a quadruple junction, very high efficiency solar cells that are specifically designed for the Mars atmosphere. They sit and harvest energy all day, and then we get about a 2 minute, up to about perhaps a 2 minute flight, based upon a whole day of charging. The fuselage contains all our critical avionics. It contains our batteries. We are one of the few projects where even aerogel was probably a little too heavy for us. We made the trade, and we have gone purely with this carbon dioxide gas gap insulation. The coating on the fuselage is a very high absorptivity special film, Kapton film, high alpha, as they say, and a low emissivity. So that's what lets us harvest thermal energy during the day, also survive the night. And there's a whole bunch of heaters related to keeping everything warm and inside that. We have avionics. It's a 3-level architecture with a radiation tolerant FPGA controlling all the low-level things. We have a hot swappable low-level controllers running on an automotive-grade processors, dual redundant with hardware fault detection. And then we have what we call the navigation processor, but it's really the stuff that does all the high-level things, and that's basically a cell phone processor. All of these elements, I must point out, have gone through extensive screening and mitigations to handle things like radiation. So there's a fair amount of engineering over and beyond what the parts brought to the table. There's a whole set of flight control algorithms that run there. It turns out that flying on Mars has some interesting control challenges. You don't get the damping on the blades that you normally get here on Earth helicopters, and we kind of discovered some new things about flying in low density conditions that had to be handled by the control system. Sensors, again, in this vehicle, commercial, there's a MEMS IMU, there's a laser time of flight altimeter. We use an inclinometer to take out biases in our IMU system. We have two cameras. There's a downward looking navigation camera, which allows us to basically derive velocities, translation of velocities. And then there is your favorite cell phone camera that hopefully will let us and the rover take a mutual selfie at some point. Landing system, lightweight legs, which have been tested extensively here on Earth on different kinds of terrain. The blades themselves are a whole different story. They're extraordinarily light carbon fiber, foam composite, multiply systems. Each of those blades, each half of those blades, so there's 4 of those halves, if you put each of those blades is 28 grams, 1 ounce. So all the blades on this helicopter weigh a grand total of 4 ounces, 28 grams each, 28 times 4. We have a custom brushless motor for propulsion. It's 23 pole pairs, hand wound with square wires to get the most efficiency in the system. That's also an extraordinary piece of engineering there to get that to be able to fly. And we have a traditional helicopter's so-called swash plate, which basically allows the blades pitch to be controlled both for up and down control, so-called heat control, using something called the collective. And then there's a cyclic control which modulates the blade pitch angle once per revolution, and that gives you the moment that you need in order to tip the vehicle over and induce forward flight. Our blades run at very high speed, as you can imagine, in order to bite through the thin air. Our current operating condition for our particular expected conditions is going to be about 2,400 RPM, but we could go to 2,800 RPM. We've been very conservative on the tip Mach numbers, staying well below anything that's transonic. And with all of this, the energy, the thermal issues, and everything, we get about good 90 seconds of flight per sol. We would probably not fly every day because we'd like to have some time to digest the data, and we need to get telemetry back in order to understand exactly what happened. So our actual flight cadence will probably be once every three days on Mars. But the vehicle itself, from an energy perspective, should be able to fly every day if we could turn around things on Earth fast enough. Next slide, please. All right. A lot of this was sort of visible even in the video, but you can see where our base station is. That's the box that stays on the rover. It's got a little antenna in that crowded top deck there. There's a whole Mars helicopter delivery system that's below, which jettisons a protective heat shield, releases launch locks with various frangible events, brings the helicopter to a vertical position, latches it in place, and does a final release event. Lots of pyrotechnic and frangible activity related to release. Next slide, please. So it's going to be a busy month on Mars. In fact, my expectation on the timeline is that this slide will probably be happening exactly a year from now if everything goes well. We will hopefully have our, what I like to call our Kitty Hawk moment, first powered flight on another planet. And so we are constraining ourselves to take off and land in the same area. And the main reason for that is we deliberately early on in the project de-scoped active hazard detection and avoidance because the verification and validation of that would have required an extensive test program and development program, and we just didn't have the resources to fight that off. So we take off and land from what I call a pre-certified site that the rover finds for us. The analysis indicates that within the first couple 300 meters of the rover driving to its science destinations, they'll be able to find a 10 meter by 10 meter spot that meets our needs. And then we just use that as an airfield and go and do our things. And the kinds of things, that's probably a typical flight path for flight number 3. And really, again, as I said, the emphasis is all on getting the engineering data to fully validate our design. Next slide, please. So where does this take us? We have running in parallel a 3-year effort of looking at Mars science helicopters. It turns out that with improved aerodynamics and being less conservative on some of the ultra conservatism we built into the operating points on the thrust curve and so forth, a similar size vehicle, what we call as an advanced tech demo design, could actually scale up well beyond 2 kilograms, even up to about 4.5 kilograms, and carrying about a full kilogram of science. And that's the kind of helicopter that could serve as a scout or a companion rover or a companion lander. You could imagine it being used to, ferry some samples back and forth for further analysis by a lander. That's an advanced tech demo design. It would be basically the same size, but beefed up in terms of aerodynamics and battery technology and so forth. There's also a more advanced design, which is a full standalone science craft, and that would be in the 20 to even up to 30 kilogram class, and that could carry anywhere from 1 to 5 kilograms of science payloads. That would be a hexacopter design. Once we have, full validation of aerodynamics models and we understand any nuances of flying on Mars with our tech demo, we believe we can, look at other kinds of configurations like hexacopter designs. So these designs are work is well underway, both at the Jet Propulsion Laboratory and at NASA Ames, and AeroVironment, which is the company that helped us build the rotor systems. And so these are the kinds of future which, if there's a successful tech demo next year, you can imagine that sometime later in the 2020s, we could have some of these craft also flying on Mars and doing science. Next slide, please. And what kind of science would they enable? There is obviously the imaging intensive sedimentology and stratigraphy. Those bigger vehicles can potentially travel, 100-kilometer type things. They can access steep slopes. We can go look at all the polar and mid-latitude volatiles where there's a lot of climate history. There's near-surface ground ice, so we could send these helicopters to go look at that. We can even fly up and down in the atmosphere to investigate, what's happening in the boundary layer of the atmosphere. So this is sort of vertical profiling. We can fly to many hundreds of meters if needed. A tech demo only is going up to about maybe, normally about 3 to 5 meters and maybe up to 10. We may open up the leash a little bit on that, but future helicopters can go, in the hundreds of meters. There's astrobiology, where we can perhaps sterilize these things extremely well because they're fairly small, and then go look for signs of extant life. Or there's magnetic surveys, which you can use for geophysics, and there are all these special regions that as I was mentioning, where you could send these systems to up close. So we are actually having a white paper for this whole planetary decadal process, and so these are the kinds of things that we are fleshing out as part of that effort. With that, I think that's my last slide, Tim, and so I can turn it back to Tim.
Okay, thanks, Bob. Excellent talk. We're going to hold questions, as we mentioned earlier, till the end of the session. And so we're now going to move right ahead here to hear from Ken Hibbert of Johns Hopkins University APL. Ken has a description of his technical background in his chart, so I won't say much about that. Rather just to make a few personal notes here that I first met Ken about 12 years ago when we worked together on an outer planet program jointly with ESA, which really laid the groundwork to the ESA JUICE mission that we have today, and also the JPL and APL collaboration on the Europa Clipper mission. The other thing I'd like to mention is that Ken is a very active member of the IPPW and has been working with us on the putting together this seminar series. So Ken, it's all yours.
Thanks, Jim. I appreciate the intro. Hey, everybody. So Jim did ask me to start with a short bio. So briefly, I began my career at NASA Goddard, where I focused on heliophysics missions. I moved over to Johns Hopkins APL because I really wanted to become more involved with planetary exploration and was privileged to work on both Messenger and New Horizons. I came to focus on project system engineering and have been involved with the formulation of various missions, proposals, and studies, including Europa Clipper, the Venus Reconnaissance Orbiter, the Type Mare Explorer, and DART. So some of these have gone on to become real projects. Many end up being proposals that fill a bookshelf with dust. Nonetheless, they've all been educational and quite engaging. I've been fortunate that starting in February of 2016, I was part of the core group that came up with the initial idea that was then evolved and turned out to be Dragonfly, and I've been working on that project ever since. So I do want to quickly acknowledge a few of the many people that contributed to much of what you're about to see related to Dragonfly. And you see here a picture of the team from our project kickoff meeting last fall. So with that, let's talk a little bit about Titan. Titan is Saturn's largest moon. However, it is also right at home amongst the planets in many ways. It is larger than Mercury. It is a little bit smaller than Mars. It does have the second highest surface pressure of all solid bodies with atmospheres in the solar system. Some of its specific attributes that are relevant is that a Titan year is about 30 Earth years. A Titan day is about 16 Earth days. Its gravity is 1/7 that of Earth, and its surface pressure is 1.5 times that of Earth. So this graphic is intended to illustrate a comparison of Titan's atmosphere to Earth's, and you can see how much farther out the Titan atmosphere extends. You can also see that comparatively there is very little, if any, precipitation per year, and you also get an idea of the relative scales of the landforms on Titan compared to those on Earth. So why do we want to go to Titan? Titan offers the next step that answers fundamental questions. Specifically, we hope to answer what makes a planet or a moon habitable, what chemical processes lead to the development of life, and has life developed elsewhere in our solar system. To answer these questions, we're bringing along a series of payloads and instrumentation, starting with a mass spectrometer. So our mass spectrometer has strong heritage from SAM, which is part of the Curiosity rover, as well as MoMA, which is part of ExoMars. We have a drill and pneumatic transfer system that is used to acquire and move materials from the surface up inside the lander for science investigation. We have a gamma ray neutron spectrometer, as well as our own neutron source, because galactic cosmic rays will not penetrate the Titan atmosphere and make it down to the surface. We also have a geophysics and meteorology package where there are sensors for wind, temperature, methane, E-field measurements, as well as a geophone and seismometer that are strategically distributed throughout the vehicle. And of course, we have a set of cameras that include microscopic downward science cameras, as well as pan cameras that live on top of our gimbaled HGA that will allow us to survey the terrain and the environment around us. We're fortunate that Cassini really revealed to us where to look for the answers. We know that Titan has diverse surface materials and environments. We know that it has Earth-like variety of geologic processes. And so the challenge really became, how do we get these science instruments to the multiple high priority sites on the surface where we want to make the measurements? And it became clear to us early on that mobility was really vital for enabling the mission. So our response to providing that mobility is to take a landed science platform and incorporate it with aerial flights. Heavier than air mobility is extremely efficient at Titan. Titan's atmosphere, with its 4 times denser environment, reduces the wing or rotor area required for lift. And its gravity, being 1/7 of Earth's, reduces the power required for flight. I'll talk a little bit more about that. In fact, all forms of aviation are easier on Titan. You've seen that historically in a number of ideas and concepts that have involved montgolfiers, hot air balloons, aircraft, and rotorcraft. In fact, a human could put on wings, flap their arms, and fly on Titan. So I also wanted to give a sense of scale. A lot of people originally think of Dragonfly as a small handheld drone or something you can wrap your arms around. In fact, it's actually quite large. You see here a picture of Dr. Turtle, who is our PI, holding a full-scale rotor. In fact, Dragonfly is strikingly similar in size to MSL or the Curiosity rover, and also, for another reference, akin to a Mini Cooper. So some of the key aspects to Dragonfly's approach to flight has to do with how we accommodated the Titan environment, how we specifically designed the rotorcraft, our surface traverse and scouting strategy, and then our use of terrain relative navigation and safe landing site assessment. So Dragonfly takes advantage of Titan's environment. I've already talked about the dense atmosphere enabling mobility. However, it also enables our EDL. In a graphic that I stole from Mike Wright, you can see here the nominal EDL timeline for Dragonfly, and then the EDL timeline from MSL to scale. And so you see where Dragonfly's EDL sequence will take just under 2 hours compared to the Mars EDL timeline, which is on the order of minutes, that we have much more time between events. And so this makes EDL for us more benign and a bit more forgiving. Not that EDL is ever easy, we don't mean to imply that, but the timing of it makes a lot of the sequencing and the events that take place a bit less critical. Additionally, the atmosphere provides protection from radiation on the surface. So we don't have to worry about designing for high radiation environments and can avoid problems that missions like Europa and so forth often are challenged with. The 16-day TSOL allows us to have a relaxed operations cadence. Basically, we get a week on Earth where we will be conducting active investigations during the Titan day. And then the following week, when the vehicle is hibernating through the Titan night, the folks on the ground can basically be planning for the next active period. And so we can do a week of active, a week of planning, and just alternate. And so we don't have to get on to Titan time or equivalent of Mars time or anything like that. The dense atmosphere, coupled with the length of the day, creates relatively calm conditions at the surface. There's very little variability in temperature. In fact, the delta T we expect is on the order of about 1 Kelvin, even with day-night terminator effects. Additionally, the environment that we're going to experience has been well characterized by Huygens because Dragonfly happens to arrive almost exactly 1 Saturn year after the Huygens descent. The low temperature, which is about 94 Kelvin externally at the surface, enables passive cooling for some of our key elements. So some of our instrument sensors can be mounted externally to the vehicle, and we no longer need to carry heavy, expensive cryocoolers. Additionally, the cold temperature helps us to maintain the sample integrity in its delivery from the surface into the vehicle and instrumentation package. So one of the early parameters we looked at right away when we decided we wanted to fly was the ideal hover power. It actually takes more power for the vehicle hover than it does for forward flight. And you can see that the ideal hover power is a function of vehicle mass, gravity, the atmospheric density, and then the rotor area. So for a fixed mass and rotor area, or examining the same vehicle in different places, you can see that the power required to hover on Titan is 1/40th that required on Earth and 1/80th that required on Mars. So kudos to my colleagues with the Mars helicopter. That's going to be an incredible flight and something I'm really looking forward to because it's extremely challenging. Now, Dragonfly's flight regime is actually in a well understood place. It's very similar to that of ultralight aircraft or airplanes and wind turbines on Earth. When you couple that experience and knowledge with modern control electronics, it really makes a multi-rotor vehicle mechanically simpler than a helicopter. And you can see that with the recent proliferation of quadcopter drones all over Earth, right? Amazon wants to use them to deliver packages, and people have toys and racing drones that are quite common today. All of this combines and also helps make our system relatively straightforward to test it on Earth, and we really can employ a test as you fly program. So in addition to accommodating Titan's environment, Dragonfly is specifically designed for that environment. We're powered by a radioisotope thermoelectric generator. There simply is not enough solar energy that reaches the surface of Titan to enable the mission. In fact, the MMRTG itself does not provide enough power for us to use it for real-time activities. Instead, we use it to charge a very large battery, and then we execute all of our flight and science activity off of that battery. The RTG does produce about 2,000 watts of thermal energy or waste heat that we use to maintain a nominal thermal environment inside of the lander. The lander body itself is encapsulated in rotocell foam, and that traps all this waste heat inside. And so all the interior components experience an environment that ranges from roughly -40 to +10 C. The dense atmosphere, in addition to enabling flight, also helps enable pneumatic sampling. So we essentially use the equivalent of a shop vac to move material from the drilling sites down at the surface up inside the vehicle where it can be fed into our mass spectrometer and instrumentation. Also, because we don't have a fleet of spacecraft orbiting Titan or Saturn, we need to utilize direct-to-Earth communication, and we've identified that an X-band link is most efficient for penetrating the atmosphere and yet returning a high bandwidth of data. So talking a little bit about the sensors and actuators that make up our rotorcraft or mobility system, I'm going to start with the sensors where we have nav cameras that take images of the surface that feed into our TRN processing. We have standard MIMUs that provide the IMUs. We have a radar, which is actually the same radar system used on both Phoenix and InSight that provides altitude and velocimetry measurements. We have a set of ultrasonic altimeters that do finer surface altitude measurements as we come in for a landing. And then we're using a flash LiDAR to help with our safe site identification and our landing process. In terms of actuators, we have 8 rotors that have been specifically designed for Titan. So these are custom rotors where Penn State University has been helping us design the shape and camber and so forth. And we have a set of custom designed motors. They are brushless DC motors that have been designed and qualified for the Titan environment. So they can be stored at extremely cold temperatures, heated back into an operational range, and then produce the necessary torque we need for flight. And you can see in the photograph on the right, one of our prototype motor and rotor combinations that was tested during our Phase A period last year. In addition to the sensors and actuators that make up the hardware, we also rely on a set of onboard processing, which includes a navigation filter and what we call a flight mode manager, both of which reside in a RAD 750 processor and provide the flight control outputs that control the rotor speed and the directionality of flight. And that is supported by our optical TRN and safe landing site assessment algorithms that reside in an FPGA-enabled navigation coprocessor. So I've talked a lot about kind of the global Titan environment. However, to really operate at the surface, we needed to have a good understanding of our local environment. So Dragonfly intends to land in the Shangri-La Dune Seas just southeast of Salt Crater. And you can see on the left a radar image of the Titan surface in that region, and you see these long, wide dunes. And in fact, the best analogy we have to that environment on Earth is from the Namib Desert in Africa. And again, you can see the dune crests with these wide inner dune regions. On Titan, we expect the spacing between dunes to range from 2 to 4 kilometers. It's not perfectly uniform, but our design approach accommodates that variability. Additionally, you'll see that we do get diversity of material between the dunes and the inner dunes. And in a close-up of what we expect the inner dune regions to look like, you'll see that it's wide, relatively flat, and free of hazards, which makes for an ideal landing spot. So with that context in mind, we've developed our surface traverse and scouting strategy, which we affectionately refer to as our leapfrog. When Dragonfly first lands at Titan, we're going to touch down in what we call landing site 1. Our initial flight will probably just be straight off the ground. We will check out the performance of the vehicle and go through a series of commissioning flights. When we're ready to actually move, we will go from landing site 1, go out, scout a candidate site, and then come back to where we started. So again, we're landing in a known spot. The data from that candidate site, which includes imaging of the terrain beneath us, will be downlinked to the ground, and that way the scientists and the engineers can pore through it and determine whether or not that is truly a place that we want to go to for a new landing. Assuming that it is, and we get the approval from the ground, in a subsequent flight, the vehicle will then look to execute our leapfrog. So we'll take off from a known site, we will fly over the previously scouted site, continue on, scout out a new location, again, collecting the appropriate imaging and data, come back, and then land in the previously scouted region. This way, we always have ground in the loop, and we are always landing in a site that has been imaged and assessed to be safe before we go there. It also allows us to employ a crawl, walk, run strategy for becoming comfortable with flying a new vehicle in a new environment and a new location. To move from location to location on the surface, we employ our own variant of terrain relative navigation where we use image-to-image correlation. And what you see here, the black triangles represent images that were taken and stored on board during a scouting flight. And then the next subsequent flight will take off and correlate to those images to get onto our right heading. At some point, the altitude varies from the scouting flight too much that we can't correlate to the previous images. So instead, we use direct image-to-image correlation. So the field of view on the surface actually overlaps. So what is in our current image overlaps with the images taken just moments earlier. And so we can do image-to-image correlation as we traverse out and conduct scouting of a new candidate site. On our way back, we will correlate to the images taken on the way out. And so we refer to these onboard stored images as breadcrumbs. So much like Hansel and Gretel, on our way out, we lay out the breadcrumbs, and then we use those to navigate back to know we're going to the right place. We come down towards our new landing site, and as we get close, we can once again correlate to the images from the scouting site and then safely land on the surface. This is a still of our TRN process where you can see our current image. It's kind of reshaped and sampled and fed into a correlation matrix. It is compared to either a previous image from the current flight or a breadcrumb stored on board from a current flight or a previous flight. And then we were able to do feature tracking into image-to-image correlation. And you'll see the result here, which displays a comparison of the true state to our TRN dead reckoning. One thing to note is they do not perfectly overlap, but that's okay because right now we're designing for robustness, not precision. If you imagine you're in a small aircraft like a Cessna and you're flying over a highway and using that to navigate, it doesn't matter if you're flying exactly over the highway, slightly left or right. It only matters that you're traveling in a proper direction and reaching the right destination. We've performed a variety of tests during our Phase A campaign. And so what we worked with is what we call our drone box. It is a camera and IMUs and other sensors combined with a commercial processor that hosts our algorithms. And we've been able to test our onboard TRN solutions. And you can see in the image to the right that we actually have really good agreement between our onboard solution and that of GPS here on Earth. Now, of course, in addition to making it from point A to point B, we also need to be able to safely land. So we defined our safe landing site threshold as a surface with 10-degree slope or less, hazards that are a quarter-meter radius or less. And we use a flash LiDAR to identify safe landing sites on the surface. Moving left from right, what you'll see is the truth map. And then this is the projected frame of the LiDAR that progresses as we fly over the surface. We can generate at 10 hertz a measured elevation, a deviation map, and then a slope map and hazard distance are produced at 1 hertz. And what you see here is the terrain beneath us and then identification of our landing sites in priority order. This is what the landing sites translate to, where we can assess slope as well as radial distance from any hazards. We'll choose the best site and settle in for a landing. So this combination of sensors and actuators, onboard processing, and a custom design for the environment allows Dragonfly to fly near the surface of Titan, where we plan to traverse up to 40 different flights and aggregately 10 to 15 kilometers per flight. In addition to moving across the surface, we also will be able to gently touch down and then deploy our high gain antenna so we can communicate to Earth. In fact, most of the time during the mission, Dragonfly lives on the surface because that's where we conduct our science. And so we only intend to fly about 30 minutes once a month. So in just about 3 years, we expect to fly about 40 times, but a preponderance of the time is really spent on the surface conducting the science and then communicating that critical information back to Earth. And with that, I believe that's my time, and I'll say thank you.
Okay, thank you so much for that excellent presentation. So we're now ready for our last presentation of the day, and that's by Jeff Hall of JPL. Jeff has been working on planetary balloons and aerobots for over 20 years, and that work has included many prototype vehicles and atmospheric flight tests. Jeff currently serves as the Deputy Manager for the Robotics Section at JPL, with an additional duty as the Space Robotics Assistant Program Manager in JPL's Planetary Sciences Directorate. Jeff?
Sorry, I had to figure out the mute button here. Let me go back and share my PowerPoint slide. All right, is that visible, Jim?
Very clear, very good.
Okay. Well, hello everyone. We're going to shift to talking about Venus now, and it's a very different kind of place to fly, and as you'll see, it involves a very different kind of vehicle. Jacob mentioned that this is the spot of the original planetary flight. And so my talk today is going to be both a look backwards into history and a look forward in terms of what some of us would like to do in the future for Venus. So this is a different kind of talk. There is no new Venus aerial vehicle mission on the books, unlike the last two talks you heard from, but we hope to change that in the future. The Venus environment is highly varied. It has a very thick atmosphere, many tens of kilometers in extent. You heard from Jacob earlier that the surface is extremely hot. It melts lead. But when you get up to the cloud level, which is, around 45 to 60 kilometers, you encounter much more Earth-like environment. So the temperature is Earth-like, the pressure is Earth-like. The clouds are made out of sulfuric acid aerosols, which is an important engineering challenge to design a vehicle to survive that. So in terms of aerial mobility at Venus, you really have two choices. You can either fly near the surface, like we heard about for Mars and Titan, but you have to tolerate 460 Celsius temperatures. And we don't have the technology to do that right now. So most people talk about flying in the Earth-like temperatures in the cloud layer. And it turns out there's all kinds of important scientific questions that can be answered by flying in that region. And that was one of the motivations behind the Soviet Vega mission in 1985. They flew two balloons. This was on two separate entry vehicles. They were carried as piggyback payloads on the Vega 1 and Vega 2 landers. These were small, short duration balloons. So we're not talking about powered aircraft or heavier than air flight. These are buoyant vehicles. And they were helium-filled pressurized balloons that were about 3.5 meters in diameter. They were made of a Teflon-like material so that it would survive the acid. Carried a very small payload, about 7 kilograms, and they floated around a 53-kilometer altitude, although as the graphic in the lower right-hand corner shows, there were some small altitude excursions due to local turbulence. The temperature at that altitude is 50 Celsius, so kind of warm, but much better than 450 Celsius. These balloons were autonomously deployed and inflated while under parachute descent. They deployed in darkness, but a characteristic of the Venus atmosphere in the clouds is that there's very high ground relative motion, typically 60 to 70 meters per second. So these balloons actually traveled many thousands of kilometers across the surface of Venus and emerged into daylight about 32 to 34 hours after the start of the flight. The balloon lifetime was long, but there was only sufficient batteries on board to transmit for about 46 hours. So these were short duration missions that nevertheless yielded a lot of valuable information in terms of wind speed, illumination levels, temperature, pressure. So they were both successful, highly successful. Not surprisingly, in the wake of this success, a lot of places, including JPL, started looking at, well, what do you do for an encore? What should the next kind of aerial vehicle exploration of Venus be? And much like on Earth, where there is a tremendously rich variety of buoyant vehicle concepts and designs that have flown, people came up with all kinds of ideas for Venus. So you could talk about, just bigger and better versions of the Vega pressurized balloon. People came up with ideas for phase change fluid balloons that would altitude cycle autonomously. You could do traditional scientific balloons that are unpressurized and they control altitude with ballast drops and gas venting. You could have solar heated hot air balloons. You could have motorized blimps. And you could have variable altitude balloons that use pumps and motors to change altitude and buoyancy and not ballast drops or gas venting. And you see pictures along the bottom, lots of prototypes made, lots of testing done. JPL in 2006 and 2010 proposed discovery mission concepts called Valor. The PI was Kevin Baines of JPL. We adopted sort of the Super Vega idea. These were large pressurized helium-filled balloons that would have floated at about the same altitude as Vega did, but would fly for weeks, not just a day or two. And given the high wind speeds, it would actually circumnavigate the planet every 4 to 5 days. The idea was to carry mass under the balloon between 45 and 100 kilometers. The second proposal upscaled. And of that, you would have 10 to 20 kilograms of science instruments. So these would be very capable exploration platforms. We built prototypes. I was heavily involved in that effort. We tested them in the lab. We actually did a successful helicopter drop experiment for the aerial deployment and inflation process. We ended up not completing the technology development. Funding is always an issue. And actually our work in this area mostly ended in 2014 with the technology development process incomplete. A few years ago, Jim Cutts actually was the lead of this. NASA sponsored a new study that tried to reassess the use of all kinds of aerial vehicles for Venus. Sort of, let's go back and revisit our assumptions. Let's fold in the latest developments from across the world. And what do we recommend? What makes sense for future Venus aerial vehicle exploration? Jim put together a team that included scientists, engineers, and technologists, and this was NASA people, professors, and industry people. The main conclusion of the report was that the class of buoyant vehicles known as variable altitude balloons seemed to occupy the sweet spot of the trade space. where by changing altitude and not staying at one fixed altitude, you could really increase the science return. And the conclusion was that could be done at moderate risk because there are terrestrial examples, and most notably the Google Loon balloon that you see in the lower right-hand corner there, that were already doing it very successfully on Earth. And this is a case where they're using pumps to move gas around to change buoyancy. And with solar-powered vehicles, you really have no consumables like ballast that run out, and so you can tolerate very long flight lifetimes. And so JPL basically adapted this conclusion, and we started poking around at this a couple of years ago. We wrote a paper last year and presented it at the AIAA conference. You see the paper number here, which tried to look at the many different flavors of variable altitude balloons and narrow it down to the one that we thought was worth pursuing. In parallel, our friends and colleagues at Thin Red Line Aerospace up in Canada have independently been working on a version of this concept, and you see the picture, the wonderful picture on the right-hand side there, where they have a kind of balloon where they can essentially compress or expand this stack of balloons and achieve exactly the same kind of buoyancy modulation that is needed. So, you know, the whole idea is that in order to control the altitude of a balloon kind of vehicle, you got a couple of choices. You either have to compress the helium so that you are less buoyant, so you go down, and then release the helium so you go up. Or you can pump outside air into your vehicle into a separate compartment, which effectively adds weight and gives you the same effect on net buoyancy. And the Google Loon vehicle actually pumps air into an internal compartment. The problem at Venus is that the Venus air tends to come with sulfuric acid aerosols when you're flying in the clouds, and mostly you don't want to be putting acid inside your structure. So it raises the question, you know, there's a lot of ways you can do this, and what method is best, you know, in terms of vehicle mass, energy consumption, and altitude range. So that's the question our paper last year tried to address. We looked at sort of the 5 leading concepts where you're either pumping helium or you're ballasting with pumped air, or you have the thin red line, you know, mechanical compression concept where you squeeze the whole balloon. So we did a fairly careful study looking at all of these different flavors, and you can go and pull up the paper at your convenience if you want to read the details. The bottom line was the pumped helium concepts and the mechanical compression concepts had the lowest mass and the least energy to change altitude. And they also did not require the ingestion of sulfuric acid-laden gas. So we have adopted those as the leading candidates for Venus. In our study, we looked at a 52 to 62 kilometer altitude range, which covers most of the clouds. You'd love to go lower, but already at 52 kilometers, the air temperature is 60 Celsius, which is probably close to the limit of currently available instruments. I think it's easier to engineer a balloon that can go hotter than it is to re-engineer scientific instruments. We targeted 100 kilogram carry mass in the study, but the physics says you can scale that up or down as you need to. All new Venus Aerobot options require development to get to TRL-6 and so be ready for flight. I think really the key to that is you need to build prototypes and you need to fly them on Earth. The 0 to 10 kilometer altitude on Earth is comparable to the clouds of Venus, so you can do a very good job of matching atmospheric density. You do a pretty good job of temperature. But it's also clear that you need flight simulation and design tools that you can use. You want to validate them with Earth flight testing and then extrapolate them to Venus. And JPL has developed a tool in the last year plus based on our DARTS lab software framework, which has already seen extensive use for EDL applications. And I'll say currently that we are working to do some early subscale prototyping of these kinds of variable altitude aerobots, and we're trying to get a handle on the configuration and manufacturing issues. And we are on track to do some initial laboratory testing later this summer. The Venus Exploration Analysis Group, the so-called VEXAG, has recently updated its strategic planning documents, one of which is this goals, objectives, and investigations document. It lays out the science case for all kinds of Venus exploration, and it includes, what you can do with aerial vehicles and variable altitude aerobots in particular. So there's a good correlation with what this platform can do in the future. A lot of it is pretty straightforward. You're interested in atmospheric composition. You're interested in the winds and the waves and the cloud chemistry, solar IR energy fluxes. You'd love to look for remnant magnetism in the crust. And as many of you know, there are concepts for actually detecting seismic activity on the surface through coupling of the ground motion to generating acoustic waves in the atmosphere. And that is a very exciting possibility that is being pursued by a number of researchers. So just to wrap up, and this is my last slide, we think that what makes sense for the next aerial vehicle at Venus is this kind of variable altitude aerobot. We want to float. You can get very long flight lifetimes and you don't need to land. We are working on concepts. We're trying to push the maturation of the technology forward. And we really hope to have it ready to go to meet mission needs in the next decade. That'll be covered by the new decadal survey. So that's it.
Well, thank you, Jeff, for that excellent presentation, and thanks to all our presenters here today. At this point, we're going to turn to questions, and I'm going to hand things back to Jacob to manage that part of the process.
All right. Thanks, Jim, and thanks to all of our panelists for giving 3 excellent talks. So I'd like to have our first question go back to Bob. So Bob, this is a question from Raj, and the question is, how do you deal with forward contamination issues?
Yeah, so there is it's a combination of various cleaning and heat sterilization techniques, and they are done at all stages of assembly so that before anything gets encapsulated or 2 pieces get glued together, there's a cleaning of all the surfaces, and where applicable, there can be temperature sterilization bakeouts, and then all along the way it's a closed loop process in the sense that there are swabs that are taken of all the surfaces and spore counts established, so that it's a closed loop process, which at the end of the day, as the system goes from component to subsystem to system, it stays clean.
All right, thanks, Bob. Another question for you. This is from Matt Domingo. Are the effects of high-speed winds in low-pressure environments well understood? Are they partially comparable to lower speed winds at Earth-like pressures, or does it cause instabilities in the lift with rotating blades?
Well, first order answer is, of course, the Martian got it wrong with the density being what it is. 100 mile per hour wind on Mars is equivalent of a 10 mile per hour breeze on Earth. Now, there is inflow effects as the rotors interact with the air. And we built a low pressure, low Reynolds number wind tunnel specifically for testing. And we are good to air speeds in this particular tech demonstration vehicle to 10 meters per second, and that's been fully validated by our wind tunnel experiments we did for the system. And we will find out more as we get on Mars, and some of the later flights on Mars will probably be in a higher wind if that becomes available. First flights will be in low wind speed, just to make sure we understand the behavior without the complication of wind.
All right, thank you. This is a question from, sorry, I'm going to probably slaughter the name here, Yochi Swanaga. How was the airfoil selected for the Mars helicopter?
This particular airfoil has some history and experience with AeroVironment. They flew the Helios aircraft. It was a stratospheric aircraft, solar powered. And so they were airfoil, low Reynolds number airfoils that were selected for that. And this is a variant of that. Since then, we have done more work on more advanced airfoils that we will use in the next generation vehicle. But it's had good heritage and good performance and was adequate for what we needed for this tech demo.
This is a question from Andrew Ball. Has the Mars helicopter needed any specific developments in the batteries?
No, we use in commercial cells, but there is a lot of safety-related circuitry that basically bulletproofs the battery in terms of like overcharging and so forth. And so that was specifically engineered for this, but these are commercial Sony VTC4 lithium-ion cells that we use, 6 of them in our battery pack.
So another one from Jose Hernandez. For the Mars helicopter, could you use an RTG similar to Dragonfly, or would that simply be too heavy for Mars?
I think an RTG would simply be too heavy, but things called RHUs may play a role in the larger science helicopters if it turns out that we need it. These are small heat-generating radioactive heating units, RHUs, which 3 of them were used on the Sojourner rover a long time ago, and so those are a possibility, but there is a fair amount of overhead in regulatory and process approval and work to actually use those systems in the spacecraft. So we would make a careful determination. If we could get away without it, we would not use it. But if it turns out to be useful, RHUs, which are in the 50-gram class of devices, are a possibility for giving heat to the system, if not electricity.
And here's another question from Yochi. How many flights and how much ground coverage are planned for the Mars helicopter? And this can be on a good day or a bad day.
So we are planning on up to about 5 flights in a 30-day window, or 30 sols as they call it in Mars. And so that's the nominal plan, with about a 3-day cadence and with some time up front for commissioning and checkout. If we do better and get a better cadence going, we'll do more, but the nominal plan is for 5 flights in 30 days. And the coverage, first flight again will be a repetition of a simple hover that we have done. The later flights would probably go out, 100 odd meters and then come back.
All right, so I'm going to move to Ken now, and thanks, Ken, for answering many of these in the chat window. It was very helpful. But I'll have you answer some of them vocally here. First, this is from Ananyo Bhattacharya. Are there any opportunities for Dragonfly to survey potential cryovolcanoes or lakes on Titan?
So we don't expect to be able to make it to the seas up at the northern poles, but there is a possibility that we may find cryovolcanoes or find related science destinations in the scope of where we can go during our mission.
All right, thank you. So another question. What happens if weather changes between 2 successive flights? How does this affect the image correlations that you do?
So there are a couple things. First off, during our time on the surface, we're continuously monitoring the weather. Part of our geophysical and meteorology package assesses things like winds and so forth. And because we have a ground in the loop process, that data will be sent to Earth and factored into models and planning for the next flight. That said, we actually don't expect there to be a lot of weather on Titan. At the season we're landing, there's no evidence of rain. When Cassini found rain, it was at a totally different season for the moon. And there's been no evidence to date of any kind of weather that would interrupt our flights during the time that we will be there. There should be no impact to the imaging taken. We fly under similar lighting conditions every time. And although the atmosphere is thick, at the altitude we're at, 400 meters or less over the surface, there really isn't that much variability that we expect consistent performance the whole time.
This is from Michael Barnhart. What has Dragonfly done in consideration of ground effects from rotor wash, in particular whether dust generated by the wash could impair instrument functions or communications?
That's actually a really good question. So we're still very early in our design process, and that is something that we're keenly aware of and actively working on. A couple of things that we've seen so far is the ground wash seems to move material down and away from the vehicle. And so it's more of a recollection in cold zones. We are trading off different mitigations for the cameras and the instruments. Obviously, covers are something we're looking at. In phase A, we had really good results for coating our windows and then having them electrically grounded. And we found that there was less than 10% obscuration or coverage of those windows over full life tests. So we're looking at a couple of different ways of mitigating those concerns. Additionally, we actually want to use the rotors to do saltation experiments. So we actually want to use the rotor system to move material beneath us as part of a science investigation. But there's a lot of work and analysis to go, and we're still pretty early on.
This is another question about TRN from Matthew Givens. Were there any challenges for the TRN system related to smooth, i.e. feature poor character of the terrain or opaqueness of the atmosphere?
Absolutely. So we worry more about featureless. I look at the images, and with the naked eye, they don't look any different to me. It's amazing what a computer can actually discern in the TRN algorithms. We've done testing so far over terrains such as deserts and new, fresh snowfall that doesn't have, features like plants or shrubs, because we don't expect those on Titan. But it's still able to pick out variability in patterns in how the sand or the snow lays, and it can identify features and navigate with those. So, so far we've had really good performance in the testing that we've done, but that is a concern and something that we're working to make the system robust against.
Here's another question from Yoshi. How was your airfoil selected?
So our airfoil, it's a custom designed for Dragonfly. Basically, right now, it's a conceptual airfoil. It's probably not the final one that we will fly with. We still have years of development to go. But our design so far has been based upon momentum and blade element theory, and then we use C81 generated airfoil tables to come up with a nominal design. And we've been working to validate that using ROT CFD, which is a rotorcraft CFD program, and STAR CCM modeling, CCM plus modeling, to validate the performance theoretically in a simulated environment.
And what do you expect to be the total lifetime of the lander? And how does that compare with the Mars helicopter?
So our nominal mission is right around 3 years. And so during that time, we expect to be able to do on the order of 40 flights, plus or minus, depending upon how far we choose to go each time. Assuming that we survive all of the initial design, we land successfully, and the system all performs as expected, we really have no life-limiting items in the design of Dragonfly other than RTG. Right now, the mission lifetime is going to be driven by the decay of the RTG, and when it no longer gives us enough waste heat that we can thermally survive in the Titan cold. So our expectation is, sadly, that Dragonfly will eventually freeze to death.
All right, so I'm going to move on to Jeff now. So Jeff, rotorcraft seem to have emerged as the preferred craft for exploring Mars and Titan. Is there some reason that this is not being considered for Venus?
Yeah, mostly it's a function that the surface of Venus is too hot to fly in. And so this concept of exploring the surface by landing and charging up and moving around doesn't really work for Venus. So you choose to fly in the clouds. You have winds, high-speed winds that will carry you around the planet. And so it seems to tilt the balance towards a buoyant vehicle that doesn't have to consume energy to fly. That's the path that we're going down.
Gotcha. So another question here. One motivation for aerial mobility on Mars and Titan is obviously to traverse terrain that a wheeled vehicle would otherwise have difficulty negotiating, like a dune field, for example. Are there any of these such places on Venus? And could we expect to see a near-surface rover on Venus that could maybe benefit from having a companion aerial vehicle?
In principle, yes, of course. But whatever vehicle, whether it's a rover or a companion, helicopter, somehow you've got to engineer that to operate it at 460 degrees Celsius. So that's not only the mechanical components, but things like motors and electronics and science instruments. And there simply isn't technology available today to do that. There's lots of ideas about how you can develop bits and pieces of that needed technology. So there are advances being made, but I think it's a long way off before you've got all the different technologies and pieces needed to put together a functioning mobile robotic platform that can replicate at Venus the kind of exploration paradigm that we've got at Mars and hopefully soon for Titan.
And finally, you've described that other forms of aerial platforms, such as these solar airplanes and blimps, can also fly on Venus. Are there exploration niches where they would be particularly useful?
One of the difficulties with solar-powered, heavier-than-air aircraft is that because the wind speeds are so high, those vehicles tend to be carried around the planet, and they have to spend 2 to 3 days in darkness where they're not getting input of energy. And with today's battery technology, the conclusion from the workshop of a couple of years ago is that today's battery technology is not good enough to store enough energy to keep those heavier-than-air vehicles flying through a Venusian night. So that is a limitation of heavier-than-air vehicle technology at Venus. Perhaps in the future, with better battery technology, that constraint will go away. But the best you could probably do now is to try to design a solar-powered aircraft that could fight the winds and try to station keep in the sunlight over a particular place at Venus. I think in principle you could do that, but the scientific utility is reduced because you'd be localized to just one spot at Venus, which is less desirable.
Okay, and I think that's the end of our time. Jim, do you want to close us out?
Yes, I'd just like to say a few closing words here. I want to thank all our speakers and thank our attendees for the questions they've contributed here. I want to say a couple of words about the next 2 sessions that we have. In 2 weeks, we're going to have a session on the role of air capture in exploration of the planets. And we have 2 excellent speakers, one from JPL and one from Langley Research Center on that occasion. And then session 4, 2 weeks after that, is involved in something which is particularly important to IPPW, and that is the support of our student members. IPPW plays a major role in encouraging students to enter this field, and they participate in our meetings and interacting with the professionals in a way that I think has been extremely successful. So this session will involve 5 student presentations yet to be selected. We're going to be doing that next week. And we are going to have 5 lightning presentations in the first half hour. And then we're going to form 5 separate sessions in which each of the presenters will detail their ideas in a fashion they can't cover in 5 minutes. And there will be questions. And unlike this session where the questions are conveyed by typing them in, you'll be able to interact orally with the presenters. If you want to hear more details about this, go to our website, IPPW 2020, very easy to Google, and it will have all the details. So we hope to see you back here in 2 weeks and 2 weeks after that. And thank you all again for attending today.